Hello, good evening, everyone. Welcome to One Concept, Multiple Tools, and Multiple Learnings program. And today's topic or today's video that I'm going to discuss here is about the variable forces. So, in yesterday's topics, we have learned about the constant forces, wherein we discussed about tension, then normal force, then force due to an inclined plane, and then we looked about friction. Okay, and these were some of the constant forces. Now the forces that we are going to look is, it depends upon the external parameter, and as a result of it we call this as a variable force, or I categorize them. The forces that I am going to learn, where we are going to look into it, or the simulators that we are going to look into it, are none other than the viscous force, air resistance, and then buoyancy. Okay, so these are the three forces that we're going to look into it. Okay, now let us, and spring forces. Spring force is very important. Yeah. So these are the four forces that we are going to look into it. Now let me share my screen to show you what is the simulators that we need to understand this or to work with this. Okay. So here goes the first one. The first one, you have already seen this in projectile motion. Okay, we have seen this also, and many of you would have used this also. So this is nothing great about it, but how do we use this with the air resistance? That's what we have here. In air resistance, now what do we have here? I'll show you just a moment. So we have something called a drag coefficient here. You can alter this. Okay, rest of them you can keep it as such, and only this one you can alter. And I can make it lesser over here. I can make it more. If I make it 0 over here, then definitely there's no air resistance, and I can now let me keep it at a drag coefficient of 0.04, and now let me run this. Let me click on this. Now a projectile is seen and is seen to be falling over here. Okay, now what I do is, what is the distance over here? The distance can be measured, the force velocity is here, components, distance is measured here. I can take this one here, or maybe I can take directly this one. Instead of taking this, I can take this value and I can keep it exactly crosswise at this point. It says the range is 10.62 meters and the height is 0 meter, which means the vertical height, okay, with respect to this, with respect to the ground, at this point the answer is only 0 meter over here. That's right, because if I take this one and keep it over somewhere at this point, you see at this point the range is 9.04 meter, which means starting from this crosswire to until here it is 9.04 meter. The time taken by the projectile to start from here and to reach here is 3 seconds, and this is 7.88 meters. What is the height over here? Okay, now what I will do is I'll take up this value itself. I'll increase the drag coefficient and see what happens to a trajectory in a two-dimensional motion. I kept it exactly at 0.5. Let me rerun this. When I run this once again, I see I get a projectile like this over here. Okay, so what's happened over here? The height, the maximum height has decreased, and then it does not decrease symmetrically. And secondly, the range is also decreased. Okay, let me find out what is the value here. The range here is 9.04, 7.88. Let us see whether, because we have increased the drag coefficient by half, so let us see whether this has also decreased by half. Okay, so here the maximum height was seen to be, how much was it? Which was seen to be, keep it here. This was seen to be 115.39 meters maximum height. Now let me pull this and put it over here. This is maximum height is 10.96, so it is not half of the height. Then the range here was seen to be 10.62 and here 6.47. Okay, so therefore there is no linear correlation between the value of the drag coefficient and as well as this. See, with just a simple experiment we can get this value, or maybe you can ask your student to do something like find a correlation between the drag coefficient and the different values of range. So what you can do is you can actually change the values of drag coefficient for 0.1. Okay, now put a projectile and see where does it fall. It falls at some point here. At 0 it was here, at 0.1 it is somewhere over here. Okay, is it that changes in the drag coefficient correspond to the changes in the value of r, or in the change of value of h? You can ask this question. They can start with a hypothesis based on this, and they can write an IA, and this can be their FA. So you can do something like this, especially for IB students. Okay, and at the same time, you can also get to know what are the components of velocity, what are the velocity vectors. what are the force vectors of each one of them. What you can do is, let me try this. See the values of fx and fy, how does it change, and so on. And there is one more component also here. See, if it did not have a drag component, let me make this drag component to be some higher value here. Okay, and then you look at the arrows here. See, this component f dv is now changing over here. Sometimes it was higher, sometimes it was lower. So something is changing over here. You can ask them, so why was it changing? What is changing over here? What is the relationship connecting this? How does the velocity vector change? You can question all this over here. Okay, it's a very good inquiry based material. Let me move on to the second question. Second tool. This is once again air resistance in case of a rocketry motion. In a rocket motion, as you see here, there is a rocket over here, and there is a run button here. The first thing that we need to look at, right? Let me see. Run button is here. Okay, run button is here, and rocket mass is given. Thrust is here. Rocket burn is here. Play button is here. So when I click on this play button, so what do we get here? You get something like the velocity starts increasing and then starts decreasing. So far, whatever we have learned is that velocity is decreasing and then increasing. Now, velocity is increasing, then decreasing, then coming to zero. So why does this happen? Okay, first question. And then what we can do is maybe we can change any of these parameters and ask, okay, how does this curve change? Let me change some of them. Let me say, for example, I'll take this rocket thrust to be 8 Newton, I'll take 6 Newton. And rocket mass also, I'll reduce it over here, 0.2 kgs. Let me run this. I get a different set of curve. Okay, and now I can look at, okay, why do I get a different set of curve, and why is the curve pattern not changing? What's exactly happening? Is the same thing that's happening forever. Maybe I can change it to a higher mass. I'll make it to 0.6 kg, rocket thrust to be very, very less, 4 Newton, and see what happens. So here, what is the dynamics behind it? So what is thrust? Okay, and why does it happen? And if the mass is very high and the thrust is very low, why doesn't the rocket go upwards? You can see from here, rocket mass is 0.6, which means the weight is seen to be 6 Newton, but rocket thrust is 4 Newton. Do you think the rocket will take it up? It won't take it up, because you know, you should have a force greater than 6 Newton. Otherwise, it will not go up, right? So maybe what I can do is I can make this to be 8 Newton, for example. And now see what happens. It goes to this height and falls out, right? So what I should do? I should reduce the mass of the rocket, or maybe increase the rocket thrust. Maybe I'll increase this one here, 10 Newton, and see what happens. I get a smaller triangle. Why do we get a triangle? Initially, until the rocket's fuel gets away, gets completed. So what happens is there's an increase in the velocity. When the rocket's fuel becomes zero, then automatically velocity reduces. And then still the object is moving in the same straight line. Rocket is moving in the same straight line. And after that, when it becomes zero, okay, there's no way that it has to come under the influence of the gravity, right? Okay, so this is what has been shown. In fact, the negative part of the curve is not shown, only the positive part of it is shown over here. Okay, let me move on to. Now, this is about viscous force. Okay, so we have seen air resistance. Now we will say about viscous force. Once again in VT graph. Now you have aluminum 3 mm ball, and this is aluminum 4 mm ball, and these are the different fluids that we have. So let us look at the different types of fluids and understand what's going on over here. So towards it, play, I have button here, pass, step, reset, graph, fluid 1. This is your fluid 1. I can use olive oil in the first one. And in the second one, density of ball, let me take, for example, steel only. And in the second ball, radius of the ball is already known. We can fix anything. We can put anything. For example, I can do with 2 millimeter, and then I can run this. There is a run button here. The run button is not seen. Where is it? Just give me a moment. It's here. Play. So let me click on this. Now you see, I do not know what is the second ball. Okay, I did not define this. Okay, it goes like this, but here you see it's going in this way, and you see this blue curve is showing something almost like a straight line, and this is showing like this over here. What does these curves illustrate? Okay, so you can say this is almost reaching a terminal velocity. This is something like the velocity is started to decrease. It's in a decelerating sense. It has not even reached a terminal velocity. Okay, why it does not reach the terminal velocity? You need to look at what is the buoyancy force over here. You can ask the questions regarding this. Why doesn't this ball reach a terminal velocity? What is the reason behind it? Okay, or maybe let me use the same fluid. Okay, let me use a density of the fluid to be olive oil here, and here also I use olive oil. In one of them I use 2 millimeter ball, and the other one I'll use, what did I use here? I use a steel here, right? Steel 2 millimeter, and once again I'll use steel, and I'll use a 6 millimeter, and see what difference will it make based on radius. The 6 millimeter one is showing a deceleration, while the 2 millimeter one, for some time it is showing a deceleration, and after that it reaches a terminal velocity, which means what? The velocity now depends upon the radius also. Okay, what is that you can say? Okay, does it depend upon radius, and what is the equation relating to? See, so many theoretical questions can be asked over here, and students will be able to successfully answer this provided they know the theory. And they can look at the dots over here. You can also question about dots. Why the dots are equispaced here? Why the dots are farther away located? We can ask about all these questions. Next, let me go to the next one. It's about springs. Now in the springs, there's a PHET simulation. So as you see here, there is two springs going over here. Spring constants you can vary. Spring constants is small, it becomes a flexible one. Spring constants is very large, you see it becomes a thicker one. So I hope you would have seen these kinds of springs in trains or maybe in your sofa sets, right? So there's a stiffer spring. What I will do is I'll make it somewhere over here. One of them to be small and the other one to be much larger. Keep it to the extent. Now I will add the 250 grams mass to both of them. Oh, it's only 250 grams over here, and I want to measure what is the distance it takes. So what I can do is I can take the scale, drag from there, keep it over here. Able to move? No. The max length is seen to be here 1 meter, and it goes beyond 1 meter also. Maybe I can measure this distance. Maybe around 1 meter and 10 centimeter, I think. Right? 1 meter and 10 centimeters, 1.1 meter over here. Now what I will do is I will take the same mass, I'll keep it aside. I take this one and add it over it. When I do this, the equilibrium point is at this point. Now you see, if I measure the distance over here, it comes out to be around 40 centimeter lesser. It's only 70 centimeter. Now you can ask the question, why does the displacement depends upon the spring constant, right? What is the equation which is representing that? Okay, though the same mass has been added. What do you mean by same mass being added? The pulling force is same, right? Because why should the spring extend? Because you are pulling it by the same mass. Same mass means what? M into G. That's the force acting on it. If the same force is acting on it, why does the value of K change? Right? That you can ask it across. Okay, sorry, why does the value of X change? So because it obeys Hooke's law, and you can say K1 X1 equal to K2 X2, and thereby you will be able to reason it. And you will also be able to find out the time period of oscillation, which is a conventional method which you do. What you can do is you can pull the timer here, keep the timer here, and then maybe I will add 100 grams weight here, and then made it to oscillate. I will start the timer when it reaches the extreme, and then I will find out what is the time taken for maybe 5 oscillations. Because it's all digital, it should not change, but it all again depends upon our reaction time. And as a result of it, sometimes you might make a mistake. Okay, maybe one oscillation done, second oscillation, I stopped here, 1.93 seconds. If I do it for one more, okay, I may get a different value. I can reset this. I'll be able to ask them to find out for every trial how does it happen. And if I do it something like 3 trials once, 5 trials once, now how does my fractional error or relative error reduce? What happens to my systematic error? Should the systematic error be 0? I can ask all these questions over here, right? At the same time, what I can do is, once this has been done, the time period of oscillation is calculated, then I can take, these are unknown masses. I can take this as an experiment, add this mass over here. I do not know what is this mass. Make it to oscillate. When you make it to oscillate, you see this is the line that we have. Okay, and then what's the time period of oscillation? You get to know what's the time period of oscillation. You get to know what is the spring constant by making use of this, and then you can find out the mass of the unknown value. You can do this also, right? And then, so this we have seen natural length. This is your natural length. Okay, natural length of the spring. That means what? If the mass is not being connected, this is the actual length of the spring. Equilibrium position is the mean position when the mass is being attached to it. Okay, to what extent does it go? From here, whatever length it goes, movable line. Let us say, for example, click on this. Okay, this is the length. This is the amplitude of oscillation, which we can calculate. Using the amplitude, you can find anything, right? And you can find out the value of time. Okay, if you know the time, then omega square, omega is 2 pi divided by t, and you know this value of a, you can find out the velocity. Okay, and then if you know the value of omega, you can find out the value of g, acceleration due to gravity, right? You can say T is equal to 2 pi root of m by k. Okay, and then, sorry, not acceleration due to gravity. You can find out t equal to 2 pi root of m by k. You can find out the spring constant. You can do many things over here, right? Because the value, numerical value of spring constant is not given. Only the logical comparison has been given. You can do it using this one here. It's a very good experiment to me. So we can do a lot of things using this. And you can also change the value of g. Like, for example, you can conduct this in moon. You can do it in earth and find out what is the difference between these two. Let me know whether it changes. It doesn't change because it does not depend upon the value of g. You can do it in Jupiter. You can do it in Planet X. You can do it in custom, whatever you want. You can do it over here. And at the same time, what you can do is you can take two different lengths of the spring. Then you can also do thickness of the spring. You can vary. You can do all this. Damping is equal to 0 here. Okay. Then there's one more tool here, which is for understanding the same thing but making use of the vectors. You'll be able to see the velocity vector and acceleration vector when the masses are oscillating. For example, I add this one here. You can see that the velocity and acceleration vector are always opposite to each other, right? Okay, so this is one thing which you can see. You can find out what is the gravity vector. Gravity vector is always downwards over here, right? Which is acting on the mass. And there's one more tool over here which gives you the energy. The energy graph tells you what happens to the kinetic energy, potential energy, and total energy. Pull this mass, is only one mass over here. Make it to oscillate. See, this is for kinetic energy. It keeps on changing over here. Then you have potential energy. Then you have total potential energy. And there is a total energy over here. You have all these parameters here. Now, why did it stop? Because, there was a damping over here. So where is the damping? Let me see. Where is the damping over here? There's a spring constant. There's a damping here which says none. Make it completely 0. This will not stop. Pull it. It keeps on moving over here, right? Okay, so this is what it helps you out, right? How does the damping help? What does the damping actually do? Okay, the amplitude of the oscillations keeps on reducing with time. Then we can go to lab. And in this lab, once again, you can use energy, you can use known mass, you can use unknown mass, a combination of all of them together. Okay, this is what it actually helps you out to solve problems. Okay, let me take up the next one. This is a spring simulation which is available online. It's a worksheet. Okay, you can use this worksheet. You can use PHET. There are activities which are being based on this. Okay, so either you can design your question or maybe you can take up this questionnaire, give it to them as an FA and ask them to work on this. This also will work. Okay, really a good one. Okay, someone has helped us out to do all this. So you can actually use this, give these questions and ask the students to work on this. Next comes the physics classroom. So this particularly focuses more on the stiffness of the spring and damping coefficient. What is stiffness of a spring? Stiffness of a spring tells you how stiff a spring is, how elastic a spring is, or what do you call it? It's a stiffness constant, a spring constant. Okay, so I will be able to move this one here. Okay, you see, this actually changes, which means what? It is more stiffer. And if I move it to here, it is more lighter. Now, how do you understand something as stiffer and lighter? So if I want to know, I'll take up this 4 kg mass, attach it here. Now, what's happening? If it is more lighter, then the spring's oscillation will be very, very large. Kinetic energy and the potential energy keeps on fluctuating like this, right? If I make it more and more stiff, then, sorry, not this, this one, spring one, right? If I make it more stiffer, then you see the amplitude of oscillation is not that much, it's lesser. Now, if I make it more damping, okay, so what will happen if it is more damped? Initially, it was 0 damped. Now, what will happen? So it is oscillating, and after some time, it has come to a rest, right? So which shows, okay, how the energy gets dissipated whenever you have a damping. Okay, now this is what has been shown. Next, what we do is you can try it out with the second spring in order to compare these two. Okay, let us move on to the next one. This is really interesting. So what we have is, we have two masses over here, and there's a magnet which is connected to this, which has been attached to it, so that I don't want to let it loose. And the first mass M1 is 5 kg, mass M2 is 10 kg. What I'll do is, I'll make both of them to be 5 kg only, to show you something initially. Make it 5 kg initially. Okay. And the value of G equal to 9.8, that means you are doing in Earth. The value of K is 100 Newton per meter. The center of mass is staying over here, and these are the two masses. Now what I do is, if I leave it here, if I release it, how do I release it? That's just a moment. It's here. It's a play button here at the end. Click on this play button. The moment I release it, make a note of these values over here. Look at this, like how, what's happening. Maybe let me click on this also. Show motion relative to ground. Okay, so I'll click this, not relative, center of mass. Let me do this first. When I click on this play button, now it is going down. Is the distance between the two masses changing? The distance between the two masses is changing? Nothing is changing over here, right? It is just going as if all of them are going in the same way. Now what I will do is, I will reset this. I will reset this. I brought it back. Now we will increase one of the masses. Okay, I will take this mass to be 10 kg. Upper mass is 10 kg. Lower mass, I'll keep it at 5 kg. I'll keep it at 5 kg. This is lighter, it's heavier. So this you can always guess what can happen. Lighter mass will now act on the second one, and now it will start moving down like this. That's what you assume, right? Let us see whether this happens. Now what's happening? The distance between these two, is it changing? It is not at all changing. Why is it not changing? Because M1 is pulled by gravity, center of mass is also pulled by gravity, spring is also pulled by gravity, the lower mass also pulled by gravity. All the three are continuously going with the same acceleration. So therefore, if at all if the spring has to compress, then what should happen? Okay, the upper mass should apply a larger force on the spring so that, okay, this will start compressing. Nothing is happening. Now this is applying some force. The spring is also moving. So it is like all of them are in free fall over here, right? So it's nothing but similar to elevator problem. So no change. Now let me reset this once again. Next, what I do is, let me make this to be 10 kg. So this to be 5 kg. This to be 10 kg. Because upper mass was lower, upper mass was higher, lower mass was lower. That's what we do. Now let us do this one. So what do you think can happen? Let me run this. Now initially there was a compression. Again there is a compression. Right? Third time also there is a compression. Okay, you can look into it as what is the reason behind it. Why is it there that when we have masses of this sort, okay, that there is a compression being observed? What is the reason behind it? Okay, you can look into it. Now let us move on to the next one. Single spring. Now this is a horizontal spring. So far we have been looking only at the vertical springs. Now here what it gives you is that you have the mass, damping coefficient, everything. You can also click on the show energy. So you can get to know how does the energy changes over here. Potential, kinetic energy. It should have been good if these are given different colors. One is a dark gray, the other is a light gray. So I may not be able to distinguish between these two, but maybe if you go to graph, I think using graph you might be able to distinguish, but the graph is very complex. Let me try to run this. Will this run here? The run button is not seen anywhere. Shows in terminal. No. Okay, I will just pull this one here. This itself is run. Okay, so what is it showing is that it's showing you the SHM along with the spring motion. That's what is being shown. Now the spring is slowed down, and finally I think it's going to come to rest. Why is it so? Is there a damping? Is there a damping? Damping. I think there is a damping, but the parameter is not shown. So as a result of this damping, the spiral is seen to be inward like this. Now how do I make this damping to be 0? There is no way to make it 0. Anyway, so it's a good graph. Then this is your time graph. Now what does this time graph tell you? Let me pull it once again and see what happens. I'm not going to break the computer. So I'm going to get amplitude. See this damping over here. See the amplitude is seen to be decreasing like this. And as a result of it, it's going on like this over here. The energy levels are also kept on reducing over here. Okay. Multi-graph. So all the graphs are seen together. Okay, it's a good one. But in order to visualize this, you need, it's here, it's here. Damping is here. Oh, I didn't see this. Okay, damping is here. The first part of it is there. Maybe if I make it 0 over here, and then I repeat the experiment, I think I may not get this problem. So it's oscillating continuously. Let me go to graph. See, it's oscillating continuously. It's always moving the same circle. The circle does not change, right? So this is what it helps you out. Okay, so you can understand more things, okay, and you would be able to have a clear visualization of what is energy in case of oscillations. Okay, this is all about the springs, useful for natural student. The next one, once again, is nothing but the mass and the spring. This can be connected to your mobile, and you can use your mobile to oscillate like this, and you will be able to conduct this experiment with a tablet or maybe with a mobile. And here what we do is damping coefficient is 0.05. You can increase it, decrease it, whatever you want to do it. And then displacement velocity is also, you can calculate over here. And then what I do is, let me click on display. Okay, when I click on display, what do you get here? You get a plot of displacement versus time, and it's reducing like this over here. And you see the velocity vector is shown over here, and it slowly starts reducing, right? It changes in opposite directions. What I will do is I'll make this damping to be 0. Can I make it 0? Make it 0. I need to stop for this. Let me stop and make it 0. Right. It is 0 now. Now let me run this. Nothing is shown, right? So there are two springs and there is an object kept over here. Okay. Now it is made to oscillate. Now what will happen is a question. So I oscillated like this and left it. You see the velocity vector is like this. Now why is this seen here? Because my hand shook a little bit, and as a result of it, you got that small changes over there. These things you should know. Okay, while you conduct an experiment tomorrow, while you record the readings, and if you get something like this, you should actually leave 1 or 2 cycles, and from there only you should start. Now you see you're getting constant amplitude over here. Okay, this is what you need to infer. See, getting the data from an experiment is not a great thing, but you need to interpret why are you getting like this, why there is an error, why it is now going upwards, why is it a constant, everything you need to know. Okay, so this is what we get over here. Then let me move on to the next one. So this is not a great one, but still I find this to be useful, at least to have a visualization of what's happening when a mass and a spring are connected and they start oscillating. How does the energy change? How does the displacement change? What's happening to the velocity vector? You can ask so many questions over here. Next, what is this? This is a pendulum which is connected with the spring, and this starts oscillating. It's a spring-based pendulum. What is so special about it? Usually a pendulum, let me fold this one here. Pendulum is made to oscillate only like this over here. Now what is it doing here? It is oscillating like this. It's also going like this over here. Two types of pendulum, right? Two types of motion. So not an easy task to work without, but anyway, let us try it out this. I'll pull it over here and leave it. Now what's happening? Wow, look at that. Okay, so it's going up, down, then it's changing its position every time. It's completely chaotic. Is it chaotic? Let us understand that. So we have show energy, we have Runge-Kutta solver, all this. Is there a damping there? Damping is 0. Okay, let me go to graph to see what's happening over here. See, this is what is happening. What is this now? This is your position of y. Position of y versus the x position. Is it going to the same point? No, it is not going to the same displacement over here. And also the heights also is not describing the same thing. Sometimes larger, sometimes lesser. So it's totally different over here. Maybe if you want, you can clear this graph. Now look at this, right? See, even the center point, the mean position is not this, also not the same. Mean position is also changing over here. So the question can be, if suppose if a string is replaced by a spring, then what kind of oscillations can you expect? Do you get the same way, or what is it then? Then you can say it is not so easy to solve such kinds of problems because there are multiple degrees of freedom, so not so easy to work with. Let me go for a time graph. Now what's happening in a time graph? Are you getting the same kind of oscillation? No, you're not getting the same kind of oscillation. See, there's though I have put the damping 0, you see the amplitude is completely changing. Sometimes higher, sometimes lower, sometimes lesser, and so on. It's totally different over here, right? Okay, now let us move on to multigraph. So this gives you an idea about correlation between these two, but anyway, see how nicely it has been done. Okay, so sometimes these kinds of figures are also called as Lissajous figures. Lissajous figures, and these pictures actually we use it in determining the frequency and so on. But anyway, you don't have this in your syllabus. When you go for your higher classes, maybe for your engineering or medicine and so on, you will be able to understand what are this. Okay, usually the nature is always like this. Okay, it is not the same one. So even a heartbeat will have your PQ or a cycle, which is totally different, right? Let me go on to the next one. Connection of springs. Okay, so far we had been looking only at the horizontal spring or vertical spring. Now the question is, if I have more springs which are connected either in series or in parallel, then what can happen? So to understand that, okay, these are problems like this being asked. So you can take up the spring, hold it using your mouse and connect it to the grid over here at the top. Okay, you should connect it over here. For example, if you hold it here and connect it over here, it drops down. Okay, it's not going to stand there. So you have to hold it over here and connect it there like this. Okay, now what I'll do is I'll not consider this one. I'll pull it back. Now I have this one plus sign here. I'll click on this plus sign. It means I have a duplicate one and these two are connected together. These two are connected together. Okay, now let me remove one of them first. First I'll remove all of them. I'll take only one of them. Put this mass here. Now maybe if I put it over here, I'm not interested in oscillation at all. See what is the actual length. Initially what was the length? This was the natural length. This was the natural length. When I added this mass, what was the extension? So from here to here, it went down by 1 box, right? Now what I do is, I'll see whether I can add one more mass. I have added one more mass. 2 boxes. I'll add one more mass also. It has gone down by 3 boxes. Okay. Now I will repeat this experiment. With the same 3 boxes, I'll add one more spring which is in parallel. When I do this, maybe you should take some pencil or pen, or if you're using your iPad or something, you should be able to draw the line, or maybe you should count. Okay. So how many boxes, what is the final length of the string? Okay, let me remove this one out. Let me redo this once again because I have not counted this. This was the natural length, which had 1, 2, 3, 4, 4 boxes initially. When I added this one, and this one, let me count the total length 1, 2, 3, 4, 5, 6, 7. The extension was seen to be, total length was seen to be 7 centimeters, so 7 boxes over here. If I add one more spring over here, now the load of these 3 masses has been taken by or shared by these 2 springs. Now see how much it is: 1, 2, 3, 4, 5, and maybe 6 also, or 5.5. Okay, so which means now the extension is reduced. Let me add one more. When I add one more, what has happened once again? 1, 2, 3, 4, 5 over here. Which means for the same weight that I am adding over here, the extension is changing. Now we know by Hooke's law that F is equal to K into X. What is that extension? Extension is nothing but X over there. Now for the same force, F is same, X is changing, which means what L should change. For example, if I have F to be 10 Newton, okay, X is equal to, let us say, 4 over here, okay, or maybe let us say 5 over there. Then the value of K is 2, because 2 into 5 becomes 10 over there. Now by adding more springs, what's happening to the extension? It is, if I add 2 springs, it is no more equal to 5, it becomes 4, for example. Now what will happen to K? K will start now increasing. K becomes 2.5. Earlier it was 2, now it becomes 2.5, because 2.5 multiplied by 4 becomes 10. Now let us say I added 3 springs and the value of X becomes, instead of 4, it became 3 over there. Then what should be a value of K? It will be 3.33, because 3.33 multiplied by 3 becomes 9.999, which is closer to 10. Which means what will happen? The value of K is increased. Initially value of K was 2, okay, the only one spring. When you put 2 springs in parallel, it became 2.5. 3 springs in parallel, it became 3.33. Which means as you keep on adding the springs, you see the spring constants keeps on increasing. How do you want to add? You want to add it parallelly. When you add the springs parallelly, then the springs constant of the combination increases. Don't you think this is very similar to that of your which one? The internal resistance, right? So sorry, the resistance adding, right? Resistance addition. So there it was for series resistance we had this. So this is how, okay, you will be able to relate one topic with the other topic. So though this topic is not being taught, okay, we don't have it, but I've seen some problems in IB, okay, which is very similar to this. So this would be useful. Okay, now you can do the same thing with a parallel also. What I'll do is remove this over here, 1 here, 2 here, 3 here. I've connected this, or maybe I'll remove this too. So first one, I've connected 1, 2, and 3. Next, what I can do, I can take this one here, connect it here, then take this. No, I'll connect this here. I'll connect this here, and I'll connect only 2 springs. And then again, I'll add the 2 masses over here, 3 masses, and see what's happening, right? Third mass. The spring now increases. But the same force, then X increases, which means K should decrease, right? So I can now arrive at conclusions like this. Okay. Oh, I can get this twisted length over here. Do I get the value here? I don't get the value over here. Okay, fine. Okay, I don't know why it has been given, but this is what you can do it. Okay, you can do wonders using this. Okay, next what I will do is let me go on to the next one. Now this is already running. Okay, what I will do is I'll just reset this. This I cannot do anything. It goes in this way itself. So what I can do is, right. The damping is 0, mass is 1 gram, frequency is 0 hertz. Reset the mass, critical damping, no critical damping, sorry. Make damping to be 0, 0, and resonance. You don't have beats. I do, I think I'll not keep resonance also. I don't have much into this. I'll come back to resonance later on. I'll reset this once again. Now initially there was 0. When you added the mass to it, the spring extends. Let me say, for example, to the other end of the block, you kept a pencil, and let me say there's a paper over here. The paper starts moving like this, and the pencil starts oscillating like this. So what happens? There's a trace of the pencil mark on the sheet, and that's what you see. You get a constant sinusoidal signal. Okay, normal sine wave, how do you get it? Using vibration of a string. That we have seen. Now, if I introduce damping, then what happens? It almost becomes 0. Let me do one thing. I'll remove damping, and then I'll pull this fellow a little bit more, and I'll introduce damping slowly. I'll not introduce this much. I'll introduce damping this much. Now what do you see? The amplitude becomes 0 here. Naturally, slowly it becomes 0, right? And then it comes to a standstill. Then let me say a resonance. Now what is resonance? As we all have, this year we have resonance over here. Resonance is being thought like if the vibrating frequency is equal to the external frequency, there's a huge amplitude being seen, right? So you can click on this resonance. If the vibrating frequency is equal to the actual frequency, a resonance is being seen. So what's happening? The amplitude is increasing. Okay, so that is what is happening. So this is what you call as resonance. You can also write beats, but beats you don't have it over here, and we are not going to discuss this. Let me move on to the next one. Finally, we have come to PHET. This once again in buoyancy you have this. Okay, so there's nothing but P equal to rho GH. So what it does is that, let me reset this. Oh, it takes a long time to reset. I didn't realize it. Okay, it's opening anyway. I opened it 3-4 hours before, and now it is opening anyway. So this only tells you about how to calculate the pressure when the height is changing. So you can show them very clearly what will be the pressure when the height is different. Okay. So what I will do is there are 2 controls over here. One is this tab, which you can control. The other one is this tab, where you can empty. So I will pull this one. I'll pull this one like this over here. It empties all the water in the container. Okay, you can change the value of gravity, fluid density, you can change whatever you want. I'm not going to change anything. You try it out yourselves. And then what I'm going to do is, I'm going to take this, I'm going to fill this water. If I want to fill, before filling, let me find out what is the pressure. This is the pressure sensor. I take this, I'll keep it here. Which means what? I'll keep it here. When it is not touching. If it touches, you won't get anything. If it is not touching in air, you see because of atmospheric pressure, it is showing 101.3 kilopascals. Now let me fill water here. Now the moment it touches water, now what's happening? 102, 103, 104. What's happening to pressure? Pressure is seen to be increasing. Now let me increase it to much larger. So as the height increases, pressure keeps on increasing, which you can directly say P is equal to rho GH, how does it work and so on, right? So now some of the students might argue saying that, okay, see, you increase the diameter of the water falling into it and reduce the diameter of the falling water. So as a result of it, pressure increase. So what I did was I did both of things, and then you can lift this upwards. See, when it is at this height, it's 126. When it is here, 122. As I keep on changing over here, so it does not depend upon the diameter of water that fell onto it. It only depends upon the height from the bottom to the surface of water. When I go until the surface and keep it on the surface, you see, in here, it's a different value. Okay. And this also changes, whether it changes with gravity. If I go to gravity, so change the gravity value also. Click here. I'll keep this as very high, 19.5. See, the atmospheric pressure is very high. Okay, provided I assume that there is an atmosphere. Okay, you get the atmospheric pressure only because of an atmosphere. If you don't have an atmosphere, you will not get this. Now, if I put it inside, it will be much larger. Okay. If I make it 0, 13.2 kilopascals, it would have been wonderful if there was an object, okay, which also has experiencing the buoyancy force. And as I change this, it also gives you the atmospheric pressure and as well as this one. Okay, we will have that effect, but unfortunately, I'm not a coder. I do not know how to code. I will not be able to do this, but you can, some of you can think about this and you can ask your students to do something like this. It will be wonderful. And these are the other examples. It does not depend upon the shape of the container also. So that is what it tells you. Whether the shape is something like this or maybe it is something like this, you will get the same atmospheric pressure, or maybe you can use this also. The atmospheric pressure will not change. Okay, so these are some of the examples where you can show like how does the pressure and the height variation takes place. Okay, so I think this we have come to an end to the variable forces. So on what parameters does the variable forces depend? So how do you account for it? How do you show it across the students? All this we have seen. If you like this video, do like, share and subscribe to my channel so that you'll get the updates then and there. Okay, whatever I'm doing. So I think almost we have completed with unit A1 and A2. Circular motion also we have finished. What is left behind now is work energy power, relativity theory, and then we do have collisions. We're not in collisions. So whatever is possible, okay, so I'll just try to find the simulations and put it across. This is something like this year, my way of teaching would be totally different. Because of this vacation, I thought, okay, why not I do something new? So earlier, what I used to do is I used to start solving problems from IB papers, JE papers, NEET papers, put it across in YouTube and see how it is benefiting for students and so on. This time I had a total different thinking. I thought, okay, why don't we teach using something called as a visual physics? Okay, so this is what I thought, because I observe how many other problems we solve in the classroom. Still, when the students go to the exam, they literally fail. They're not able to understand the context. Most problem is that they're not able to visualize it, imagine it. If you ask me, they generally ask me, sir, how do you actually visualize it? I visualize it because it's an experience. For nearly 2 decades, I've been teaching physics. So it should not be very difficult for me to visualize things. You give me any problem, I first think about it, how it can look for me, and then I approach. 70% of my time only goes in understanding, thinking about it, and interpreting it in multiple ways according to what is useful for me, and then 30% of it goes in writing it down. But our students, what they do is they start first thing itself, the moment they see a circular motion, sir, there should be centripetal force, centrifugal force. They put across everything, whatever force you want. They put V square equal to U square plus 2A, everything they put it across. Now this is what happens. Okay, until and unless they don't understand the problem, until and unless they don't visualize it, somewhere we need to bring in that concept of visualization, which nowadays has become very difficult with our current generation. So I thought maybe this kind of visual physics will definitely help them out to solve such kinds of problems. Okay, enough of lecture. So let me stop here and see you people in the next class. Thank you.